Hi all, let's take a look at the remainder of the problems in section 4.7 looking at optimization. The seventh problem here has us find the dimensions of a rectangle of maximum area that can be inscribed inside of a circle. And we know that that circle has a radius of 13. So what we're thinking of here is the wider the rectangle is, the less the height can be. And so if I call the horizontal here x, then the y would have to be smaller every time I tried to increase x. On the other hand, if I decreased the horizontal value, then the vertical value could increase. So it becomes a question of how large can that rectangle be if it's inscribed inside of a circle radius 13. Okay, so you see I put my answer down here. Here's where that came from. And here's what I was thinking in this problem. So I had my circle here, and I knew it had a radius of 13. So instantly I knew I needed to come up with some type of formula for the area of that rectangle on the inside. So with that radius of 13, I was able to make that the hypotenuse of a right triangle, where the height of that triangle is going to be 1/2 the height of the rectangle, and the width of that triangle is going to be 1/2 the width of the rectangle. So then I could say, well, all right, I know that the y value, for example, here, if I wanted to put the y value in terms of x, we know that any side of a right triangle is always the square root of the hypotenuse squared minus the other leg squared. So I said, well, then if I have my triangle labeled like this, then I can say y is equal to the square root of 169 minus x squared. Now, with that in mind, and I'm just going to call the horizontal side of the triangle x, then I can say, well, the area of that rectangle, if I'm going to call this x, then the base of the rectangle would be 2x. And if I would call the height of my triangle y, then the height of my rectangle is going to be 2y, or in other words, 2 times this square root. That's what I tried to reason here. I said, so the rectangle's area would be 2x times 2y. And then I can say, well, that's going to be equal to 4xy, where we know the y value is what I solved for right here, the square root of 169 minus x squared. Okay, now I have my area function solely in terms of x. So I should be able to take its derivative, set it equal to 0, find the critical points that are going to optimize this function. Cool stuff. So I think, okay, when I take that derivative, I'm going to have to use the product rule. Derivative of 4x is 4 times the second plus the first, which would be 4x. But the reason you see a 2x here is because I said times the derivative of the second. And this is a group to the 1/2 power. That 1/2 came down and multiplied the 4x to give me 2x, times the group to the negative 1/2 power, times the derivative of what's inside of that group, which derivative of negative x squared is negative 2x. So now I have my derivative formula out. I need to set it equal to 0. So I just rewrote my first term. I simplified my second term. I said, I know I'm going to have a positive, but it's part of a term that has a negative in a product. So it's going to be plus a minus. So I just went ahead and said minus, and I'll have 2x times 2x is 4x squared. And then this becomes the square root of 169 minus x squared in your denominator. Okay, now we set this equal to 0. So I know I can just move this function over to the right-hand side, and I'll have 4 on that root is equal to 4x squared over the root. Then I can say, well, all right, I can't solve for x as long as it's inside of a root. I also can't solve for it as long as it's inside of a square root. I can handle both of those. Sorry, I can't solve for x as long as it's inside of a square root or inside of the denominator. I can handle both of those issues in one step here by simply multiplying by that square root of 169 minus x squared on both sides. When you multiply the square root of 169 minus x squared times the square root of 169 minus x squared, you just get the group 169 minus x squared. Then I went ahead and said, instead of multiplying that by 4, let's go ahead at the same time and divide both sides by 4. And 4x squared divided by 4 is x squared. Now, this gave me a solution of, well, 2x squared would equal 169. So x squared is equal to 169 over 2, which led me to say, well, x is the positive square root of 169 over 2, which simplified down to 13 over the root of 2. Now, of course, we know it's only the positive root since it's the length of this side of the triangle. It has to be positive, can't be the negative square root of 169 over 2. So now, when I plug this back in, I can say, well, this is the value of x that's going to optimize this rectangle. To find the value of y, I just go back and I can say, well, I know my y value is the square root of 169 minus x squared. I plugged that x value into that. And square root of 169 minus 13 over the root of 2 squared, that's just going to be 169 over 2. And so I can say, well, 169 minus 169 over 2 is 169 over 2. And then, of course, the square root of that takes me back to that exact same 13 over the root of 2 that I got for the x value. So it makes sense. You say, well, clearly the area of the rectangle within is going to be optimized whenever that rectangle is actually a square. That's going to be the maximum area whenever the dimensions are the same. The x and y values are the same. Now, you'll notice on Achieve here that it took me 2 attempts for this problem. Well, why? Well, because the first answer, I'll put my x and my y value in there. That's not the answer. The answer is, what are the lengths of the sides? So you just need to remember, in order to work this, I had x labeled as the horizontal side of the triangle, not of the horizontal side of the rectangle. So I had to go back in and say, oh, okay, the lengths of the sides of the rectangle are 2x and 2y. Well, 2 times 13 over the root of 2, that's just going to simplify to be 13 on the root of 2. You could say, well, 2 is the same thing as the root of 2 times the root of 2. So the root of 2 divides into 2, leaves me a root of 2 in the numerator, and I have both of those values for my x and y component of my rectangle. And you'll see that's what I entered in here on Achieve, 13 on the root of 2 for both the horizontal and vertical region of my rectangle. Well, in this case, the rectangle is a square. For the next problem here, I like this one. It says in the article, "Do dogs know calculus?" The author, Timothy Pennings, explains how he noticed that when he threw a ball diagonally into Lake Michigan along a straight shoreline, his dog Elvis seemed to pick the optimal point in which to enter the water so as to minimize the time it took him to reach the ball. And so for example, if he threw the ball into the water here, the dog didn't go the entire horizontal distance on the shoreline and then swim to the ball, nor did it just say, well, I'm just going to swim the entire distance to the ball. The dog went down the shoreline a certain distance and then swam into the water to reach the ball to minimize his total travel time. So now, assuming that this dog was brilliant at calculus, we're supposed to determine the path that he took. It says he timed his dog and found that he could run 6.8 meters per second on the sand, yet he could only swim 0.88 meters per second. And then it says if Tim stood at point A and he threw the ball to point B in the water, which was a perpendicular distance of 10 meters from point C, and we know point C was located 15 meters down the shore. Okay, so what is that optimal path? Here's where I've tried to draw this scenario of the problem out. Our starting point A, the ending point out in the water. Point C is 15 meters down shore, and we know that it's a distance of 10 meters into the water from that point C. Now, we're trying to minimize the time it's going to take this dog to reach the water. So I can say, Well, clearly it's going to be time in the shore, or time on the shore plus time in the water. Now, that time on the shore could be 0. What if the dog just didn't run down the shore at all and just went straight into the water? So this portion could be 0. This portion could never be 0. There is going to be a time spent in the water. In fact, we know that that time spent in the water would be the lowest if he ran the entire distance on the shore and just went the 10 meters in the water. Anything else, and he's going to have to go more than 10 meters. So the first thing I did was I started labeling things. So I said, since we know that there's 15 meters of shoreline, let's let the number of meters of shoreline that the dog is not going to use, because he's going to bypass that amount by whatever route he takes, let's let that amount of shoreline be X. And so then that made it convenient to label the hypotenuse of this triangle here. This hypotenuse, X could go all the way out to be 15, X could be 0. But whatever X is, I can say, well, then the hypotenuse is going to represent the distance that the dog is going to have to swim in the water. And that's simply going to be the square root of this leg squared plus this leg squared. So we say it's the square root of X squared plus 100. Now, so the total time traveled with respect to X. The time on the shore, it's going to be the distance on the shore divided by the rate on the shore. Well, the distance on the shore clearly is going to be 15 minus however much of the shore he's bypassing by the route he takes. So 15 minus X is the distance on the shore divided by the rate that the dog can run on the shore, 6.8 meters per second. Now, plus the distance in the water divided by the rate in the water is going to be the time spent in the water. So time is equal to distance divided by rate. Now it's just a matter of, okay, take the derivative of this time expression with respect to X. Now, in this first one, what I actually did is I thought of this as 15 over 6.8, which has a derivative of 0, and then minus 1 over 6.8 times X, which has a derivative of minus 1 over 6.8. So that's the derivative of that entire first term just by distributing that 6.8 into each term in the numerator, then taking the derivative. In the second term, what I did here is I thought of this 0.88. You could think of that as a coefficient of 100 over 88. And then I said, okay, the 1/2 is going to come down and multiply that, and that would reduce it down to 50 over 88, which reduces down to 25 over 44. So this is just 1/2 times 1 over 88, or 0.88, reduced down to that fraction, then times the group to the negative 1/2 power, times the derivative of what's on the inside. Well, the derivative of X squared is 2X. Now I said, okay, derivative has been taken. Can I set it equal to 0 to find my critical points? Sure, I can. So I take my negative 1 over 6.8, and then when I multiply the 2X by this fraction, 2 times 25 over 44, that took me back to 50 over 44, and I'll have the X in the numerator. This becomes the square root of X squared plus 100 in the denominator. Now I set this equal to 0. Well, when I set it equal to 0, I know that that negative 1 over 6.8 can move to the right-hand side and become positive. And then at that point, all I did is I cross multiplied. I said 50X times 6.8, 340X, 44 on the root of X times 1, 44 on the root of X squared plus 100. Now, I knew I would not be able to solve this problem out as long as that X stayed in the square root. So from this step to this step, I merely squared both sides. 340 squared gave me 115,600, X squared. Over here, if you square 44, you're going to get 1936. That 1936 is going to get distributed through this group because, of course, when you square the square root, you just get the group X squared plus 100. So the right-hand side became 1936 times the group X squared plus 100. I distributed that through and got my 1936 X squared plus 193,600. Now, My goal was to solve for x, so I got my terms of x squared on the same side. I subtracted 1936 x squared on both sides. Had 113,664 x squared equals 193,600. So then, of course, x squared is equal to what we had over here, the 193,600 divided by 113,664. So x is just the square root of that expression, which came out roughly to be 1.305. Now, x is the amount of meters he's going to bypass by whatever path he takes. Let's make sure I'm answering the question. I believe that's all it asked. Yeah, that's all it asked. It was the answer X. Elvis entered the water at a distance of blank from point C. All they want is that distance X. That's what I have. And they want it, it actually says give your answer to 2 decimal places, but it accepted my answer to 3 decimal places. So, 1.31 should have been my answer versus what they wanted there, but they accepted my 3 decimal place correct answer. Up next, for number 9, it says, find the point on the line y equals 7x closest to the point 1, 0. This problem would cause a lot of confusion with students. Let me point it out here to you. So we're trying to find the point on the equation y equals 7x closest to the ordered pair 1, 0. So since we're trying to find the point closest, I was thinking, well, the distance between any 2 points can be given with our distance formula. So if you remember back to pre-cal, the distance between any 2 points in a plane is the square root of the change in x squared plus the change in y squared. So x2 minus x1 squared plus y2 minus y1 squared. All right, so since that looks like it would be pretty difficult, well, not difficult, but it would be harder to work with since it has 2 groups within the square root. It would be a chain rule problem if I tried to take the derivative, which might not be that bad. But if we're thinking about optimizing the level of difficulty by meaning minimize the level of difficulty in this problem, then you would say, hey, I don't want to work with that. And instead of that, you just say, well, clearly the distance is going to be minimized if the square of the distance is minimized. That just makes common sense. So that's what I put right here. The distance is minimized when the square of the distance is minimized. So instead of worrying about this, I just said, well, then d squared is all of this without the square root around it. Ha ha. So then d squared, the function I need to minimize, minimize the point on the line of y equals 7x that's closest to the ordered pair 1, 0. So I can say, well, then the square of the distance is the distance between the point on the line and the x component. Well, that's just going to be x minus 1, and again, quantity squared, plus, well, what about the vertical distance or difference squared? Remember the y value here, your ordered pair on your point. So this is the ordered pair I'm supposed to be close to. Well, the point on the line has to be x comma 7x. I should have put that right up here. So the point on my line, this has to be x comma 7x because the y value is 7x. So for the x value of x, your y value has to be 7x. So the difference in my y values here would be y2 minus y1, well, 7x minus 0. And then again, I'll square that difference. X minus 1 squared gives me x squared minus 2x plus 1. Of course, plus the vertical difference squared, that's 7x quantity squared for 49x squared. Combine these two and you'll get that the square of the distance is going to be 50x squared minus 2x plus 1. Now, we take the derivative of that because we need to find when d squared has a minimum. When d squared has a minimum, d will have a minimum. So I take the derivative of my expression for d squared. And I can say, well, that derivative is just going to be 100x minus 2. That's very easy to set equal to 0. I'll get 100x is equal to 2. and x is equal to 2 over 100 reduces down to 1/50th. Now I know that the x component's 1/50th. I know the y component's just 7 times the x, so easily it's 7 over 50. That is the point on the line, y equals 7x, that has a minimum distance to the ordered pair 1, 0. Done. And then you can see that you do have to enter it in as an ordered pair. The last question here, it's a good one. It gives us, it says a poster of area 15,360 square centimeters has blank margins of 10 centimeters wide on the top and bottom and 6 centimeters wide on each side. Find the dimensions that maximize the printed area. Okay, so when I'm going into this and answering my question, and let's see, and actually, I think that they've worded the question wrong here. It says find the dimensions that maximize the printed area. You'll see it took me 2 attempts to get to this answer. Now, is that because I was wrong to begin with? Oh, no, I don't think so. What I did initially is I found the area of what's inside because I thought that would be the printed area. They actually, the correct answer to this, they're wanting the area of the entire poster. That's what they want. So I'll point that out as we go into it in the problem. So here's what I drew out. The poster that they're referring to, I tried to draw out and I showed it has a 10-inch margin on top and bottom and well, I think it was actually measured in centimeters, and a 6-centimeter margin on each side. Okay, so the outer area would be, if I label X to be the dimensions of the inner area and Y to be, sorry, X to be the width and Y to be the height of the inner dimensions, then I can say, well, the outer area would be X plus 6 plus 6, X plus 12, and then the Y value, or the vertical value, would be Y plus 10 for Y plus 20. I know that X plus 12 times Y plus 20 would have to give me the dimensions mentioned, or the area mentioned, which was 15,360. So I just say, well, X plus 12 times Y plus 20, it's equal to what was given for my problem, 15,360. Now, when I work with the left-hand side, I'll FOIL this out and I'll get X times Y plus 20X plus 12Y plus 12 times 20 to 40. So now I can say, well, all right, let's get all of the terms of Y on the left-hand side, move the X terms to the right-hand side. So in this step, I just said, well, 15,360 minus 240 minus 20X, and on the left, I kept these two terms, xy plus 12y. And then you can say, well, you can factor a y out of that group and you'll have x plus 12 left over. That's precisely what I did. So I kept all y terms on the left, went ahead and factored the y out, and then put every other term on the right-hand side. Of course, 15,360 minus 240 reduces down to 15,120. I have minus 20x, but now if I want to solve for y all by itself, all I have to do is divide x plus 12 on both sides. Done. So here's my expression of y in terms of x. And so now, if I'm trying to find that inner area, I can say, well, the inner area would simply be x times y. I'm supposed to maximize that inner area. So I'll say, well, all right then, I'll maximize the inner area, but I first need to get it solely in terms of x. We can do that now. So instead of saying the area is x times y, I'll say the area with respect to x is x times what y is equal to in terms of x. So I substitute that expression in. At that point, I go ahead and distribute x through the numerator and get 15,120x minus 20x squared all over that x plus 12. And I know that this is going to be the expression for the area of the inner region that I need to maximize. So I need to take its derivative. When I take its derivative, of course, it's a quotient, so I square the denominator. I bring the denominator to the numerator, times the derivative of the numerator, minus the numerator times the derivative of the denominator, which is just a 1. After that, it was just simplifying, so I FOILed out the first two here, and that's where my first 4 terms came from. Then I know I'm subtracting 15,120x, and I know I'm adding 20x. I kind of ran out of room horizontally there. Now, all of this simplified down and combined in the next step. I had a negative 40x squared plus 20x squared for negative 20x squared. And when I combined the terms of x, 2 of them canceled out, the 15,120x minus 15,120x. So I only was left with a minus 480x. And then, of course, plus our constant of 181,440. Now, I was thinking, well, maybe this would factor, but it doesn't factor very nicely. Now, one thing I was able to do is I was able to take the greatest common factor of negative 20 out of it, and that left me x squared plus 24x minus 9,072. But then at that point, I knew that the critical points would exist whenever the numerator of this fraction was equal to 0. Well, the only way that the numerator could equal 0 is if this quadratic that's a factor of it would equal 0. In order to solve that out, I just used the quadratic formula. So I said x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then you can see I plugged it in correctly. After that, I just said 24 squared plus 4 times 9,072. I took the square root of that, and this is where I knew, hey, this was the right thing to do, because that ended up being a perfect square, and it simplified to be 192 after I took the square root. So then I just said, well, there's no way it can be negative 24 minus 192, because that's going to give me a negative value, which makes no sense for x. Clearly, x has to be positive. So I just said, well, then it's just plus the root of this, which was 192. So negative 24 plus 192 divided by 2 gave me a value of 84. And I said, all right, so then my horizontal component is going to be 84 centimeters. And then I use that to solve for y. Well, I know my y value is just 15,120 minus 20 times the x value of 84 divided by x plus 12, which would be 84 plus 12. So where I got this from is right here. I just plugged it into my equation for y, the x value of 84, and you'll see plugged 84 in the numerator and denominator, obviously. And when you do that, it's going to simplify down to be 140. Now, what I was thinking was, hey, then the area of the printed region, which you'd think the printed region would be the inside area, it should have a width of 84 and a height of 140. I put those answers in. Achieve said no. What Achieve is wanting here, and I think that the wording is off. They're wanting the whole page. So Achieve wants the dimensions of the outer region. You're going to take the width that you got and add both of the margins, 6 plus 6, so 84 plus 12 gave me 96. Same thing for the height. You take the height that you get, add both margins of 10 and 10, and you can say, well, 140 plus 20 going to give you 60. So notice the answer that they're wanting is the 96 and 160 here. So whenever they say the maximum printable area, they're really just wanting the maximum area of the entire poster. So they're just saying, what if there's no margins whatsoever? Okay, so I will stop with that since this is the last problem in this section. Please let me know if you have any questions. This optimization section is a fun one. I just hate that we only had 10 questions in the homework here. I kind of feel like we should have done some more, but that's all there was on Achieve. If you have any questions, though, let me know. I'll be glad to help. Sadly, we only have one more section left, and that's section 4.8. And it's pretty much an entirely graphing calculator section looking at Newton's method. So you'll want to make sure you have your calculator for that section, and please check out my video if you need any help with working it out as well. All right, guys, I'll talk with you later.